Welcome to Organic Chemistry. This is the first lecture in a series of lectures that reviews the basics of the introduction to organic chemistry based upon the New York State Regents curriculum. Now, organic chemistry is the study of carbon-based molecules. These are covalently bonded molecules that have a carbon backbone, and that carbon backbone is really built in photosynthesis by plants fixing carbon from carbon dioxide into molecules. And so organic chemistry is a study of the life-sustaining reactions that occur in all organisms that we understand life from. And so sometimes this is called biochemistry. And this, believe it or not, is the largest section of chemistry that exists. Um, if you've been studying chemistry outside of organic, you've been studying inorganic. Okay, and although inorganic chemistry's principles, okay, are still held inorganic, organic is especially in the idea that we're again studying these life-sustaining chemicals that are carbon backbone. Okay, any case, let's get started. We're going to start with this first lecture. All right, and I call it part one: alkanes, alkenes, and alkynes. And these are hydrocarbons. These are molecules that just have carbons and hydrogen. And we're going to learn about the nomenclature and their properties of these types of, again, organic molecules, which is, again, the largest, and I'll explain why. So let's be crazy and start with the first slide, okay, and get right into the things we have to know. All right, so here we go. So we're talking about organic chemistry. Don't worry about that Roman numeral, okay? It's, of course, the chemistry of the compounds of carbon. Okay, includes all living matter and formal living matter. Of course, we all know about this idea of our products of petroleum, coal, wood, and other plant products and animal sources that these came from. In fact, you probably learned them to be fossil fuels. So our gasoline, our diesel fuel, our kerosene, our waxes, so many oils come from past living organisms. Most of them come from phytoplankton, but people think that we're always burning dinosaurs. I'm sure there are some dinosaurs that have become part of this, but a majority of them are single-cell organisms that were once living. Needless to say, whether you're a single-cell organism or a multi-cell organism, we all use the same form of molecules which are carbon-based to live. All right, so moving back on. So in order to be an organic compound, you have to have a carbon, okay, in your molecule based on this curriculum. Okay, so moving on. So carbon has electron configuration, 1s2, 2s2, 2p2. Now, I'm going to give you this configuration, but I'm also going to tell you that I know that in the Regents curriculum, they may not use this designation. Okay, so in the Regents curriculum, they will have the configuration to be 2, okay, dash, okay, 4. Okay, for those that have taken a more higher level course, there are 2 electrons in the first principal energy, or the first shell, and then there are 4 electrons, okay, in the next principal energy level. So whether you say it's 2-4, okay, remember the coefficients are the exponent, are the the coefficients are the electrons here, or 2-4, it doesn't matter. What we're after here is noticing that there are 4 electrons, whether you know them to be 2 electrons in an s and 2 electrons in a p orbital. That's not part of the Regents curriculum, but okay, your teacher might have taught you that. The bottom line is that there are 4 electrons in the outermost shell. This is the core electrons, or the kernel. These electrons are stable, always in electron configuration. Think about the nucleus, okay, which is positive due to its protons being in front. And so by proximity, the first 2 electrons are very stable. They're controlled by this being so close to the positive. Don't forget, electrons are negative. These 4 electrons are not in a filled energy shell, so of course they are, of course, most most unstable. They don't feel the nucleus as well. So therefore, they are the ones that are available to bond. So there's 4 electrons, and you've learned that having 4 electrons in a covalent bond is not good enough. You learn about the octet rule. There's something about filling the S and P. Don't care if you didn't have that, but we want to have 8. So the octet rule is very important here. So if you've got a carbon and we do a Lewis dot diagram, you're going to notice that it's got to have 4 dots around it. We draw the 4 dots separate from each other because they repel themselves. And so in order for carbon to bond, it's going to need, okay, 4 more electrons from other atoms to fill its octet. So we learned that it likes to make 4 covalent bonds. And don't forget, the covalent bonds are the sharing that occur. Really, when we study organic chemistry in Regents, what we're studying really is an application and review of covalent bonding, right? So we're talking about carbon, and a carbon, of course, is a nonmetal, and so therefore we're really going over our covalent bonding conventions and understanding and concepts. Okay, so the key here is that the reason why there are so many more, okay, and the reason why I should say organic chemistry has it's such a larger pie of overall chemistry. And again, if I was to draw a pie chart, and I'll do my best I can here, and this little sliver probably is the study, okay, of inorganic chemistry, and then the rest of this is organic. And so organic is a huge component of chemistry because it makes so many molecules. 99% of all molecules, remember, molecules, a word describes bonding between nonmetals, right, sharing electrons because they both have a high electronegativity, right? This is a little review here. Okay, so the reason why there's so many more, like again, 99% or 99.9%, whatever that number is, okay, but generally speaking, more molecules exist that are carbon-based that are not carbon-based. Well, why? Well, because carbon can make 4 bonds. And if you have 2 carbons, well, then think about how many different arrangements you have. So you've got that 4 factorial, those combinations. So organic compounds, as you add carbons, you start adding 4 different types of bonds for each carbon, and so the number of them grows exponentially as we add carbons. So the arrangements of the carbons and how many carbons you have just adds to the complexity and the enormity of different types and of molecules you can have. All right, and if you notice, there might be some subliminal messages that come up in this presentation. So in any case, organic compounds are much more numerous than inorganic compounds because the carbons can bond to 4 things, and oftentimes organic compounds have many, many, many carbons. So as you add more carbons, you add to the complexity of the different types of structures you can have. Okay, so moving on. So characteristics of organic compounds, these compounds are all nonmetals bonded to nonmetals, thus are covalently bonded, as we just talked about. Okay, and all covalently bonded molecules are molecular solids. Again, another review word. Molecular solids are solids that have covalent bonds. Well, solids that are organic compounds are molecular solids, like glucose. Okay, another compound made by photosynthesis. Okay, thus organic compounds have the same characteristics as molecular solids, which we learned in the bonding unit of molecular solids. Okay, so in any case, that's what we have here. All right. So these compounds, again, organically speaking, are nothing more than the same things we've been talking about in terms of what we've learned previously in terms of covalently bonded compounds. So that's important as we go through this. They're not special. They're just, we're using the word organic to remind ourselves that we're doing a particular type of covalently bonded substance that we learned, and these are the carbon-based ones. All right. So moving on. All right. And again, there's some subliminal messages that may pop up here. All right. Don't take them all that seriously. Now we have the atomic radius to look at here, and we look very carefully that, again, we're spending our time thinking about that the covalent compounds are nothing more than what? They're nothing more than covalently compounds, which we know are the nonmetals bonded with themselves. And why do they have to bond with themselves? Because as you go across the period, what happens to the size of the radius, it decreases because of the increasing number of protons. We call that the Z number, or we call that the nuclear charge increases. So having more protons pulls in the electrons in closer. And what happens is, because of that, these atoms in the upper right hand corner have the greatest ability to attract other people's electrons. Again, this is just a review of what we've talked about. All right, so let's move on. So organic compounds, nothing more than these covalent compounds you learned about, have a slower rate of reaction than ionic compounds. Everyone forgets about this, okay? And you may say, Mr. Grotsky, why would they be a slower rate of reaction than ionic compounds? Well, ionic compounds have positives and negatives. And when you dissociate something that has positives and negatives, think about a soluble salt. That's like KCl. For instance, if we take we do this. We put KCl here. All right. And so if I have KCl, potassium chloride, and we know that potassium chloride is really a positive calcium attracted to a chloride, an anion, in a salt. And what happens is they dissociate into K plus and Cl negative in water. Okay, in your solubility table, all right, table F, you know that potassium is soluble. Okay, now what we know here is that potassium is the positive ion, called the cation, and the chloride ion is the negative ion. Okay, which is a little bit bigger because it when it gained electrons become negative, okay, it got bigger. But the bottom line is all you're doing is pulling apart a positive negative. There's no electrons being transferred here. There's no change of charge. And really what's happening is a water, if you put water right here, H2O, okay, this is called a dilution or an ionization reaction. Water is just competing for these charges. So ionic compounds, because there's no divvying up of electrons, always react faster than covalent compounds. Covalent compounds, as I showed you before, if I write, let's say, hydrochloric acid, a Lewis dot diagram, hydrogen has 1 valence, and then chlorine, I'll do X's, has 7, okay, valence electrons. And this is the Lewis dot diagram. You don't have to do X's and dots like I did, but I'm trying to show you that this is a pair of electrons that are being shared, okay? And when these bond, these electrons have to be divvied up some way, and that takes a little longer. When you're an ionic compound, hey, you're just a positive or negative that separates, and that's much faster in its chemical reactions than when you have to bring an electron or move electron here or there to make this work. So organic compounds, just like all molecular compounds, react a little bit slower, okay, than covalent. All right. So, any case, moving forward. All right. So, are generally nonpolar because of symmetry, okay, and are insoluble in water. Now, we say generally because organic compounds do have polar compounds. We know glucose is polar, but there's when you talk about hydrocarbons, and that's what this really easy for me to say lecture is about, okay, hydrocarbons are generally nonpolar, okay. Now they do so because of their symmetry, and because so they're insoluble. And I'm going to pull this up, and there it is. So there is an example of a hydrocarbon. Notice how many bonds we have here. Every carbon has 4 bonds because it needs to have, remember, a bond is a pair of electrons. Every carbon has to have 8. Notice hydrogen has 1 bond. It has 1 valence electron, so it's going to be a terminal atom. Okay, now we learned that if you're symmetrical, that the distribution of charge is going to be even. So there's a symmetrical distribution of charge. No side has more electrons than the other, and this is, say, very symmetrical and therefore nonpolar. Now, in truth, I have to speak because in truth, in real life, in real chemistry, any hydrocarbon you have is nonpolar because we essentially say that the pull of electrons between a carbon and hydrogen is about in the middle, okay? So generally speaking, we all talk about the fact that hydrocarbons are nonpolar no matter what their shape is, because a hydrogen to carbon bond is essentially a nonpolar bond. But if you didn't learn that, that's okay. A hydrogen to carbon bond is in the Regents curriculum considered to be a polar bond, and because of the symmetry, they're nonpolar. I know it's terrible, but we have to go there. Also, organic compounds are poor electrolytes. This electrolyte word describes how well things break apart into free ions. Remember, glucose, here's an example of a carbon-based molecule, okay, made by photosynthesis, part of life-sustaining reactions in cell respiration, is not electrolyte because it does not dissociate into free ions. Remember your chemistry. To conduct electricity, to be an electrolyte, okay, you must break apart into ions. And of course, these guys don't. Now, there are some organic compounds that can, but they fall under the same way. You should know that all electrolytes are either acids, bases, or salts. Like the KCl is a salt, is another word for ionic. So these guys do not break apart into free ions. And therefore, they're poor conductors of electricity. And they're poor conductors of heat because their electrons aren't free to move. They have strong attraction to their electrons being in the upper right-hand corner. Okay, so they pull on electrons so tightly they're not free to move, and not having a free movement of electrons gives you a terrible conductor of heat, right? The vibrational energy can't pass through the substance if electrons are held so tightly. And of course, because they don't break apart into ions, okay, they are not able to move through a solution to conduct charge as well. So they're terrible conductors. And that's why organic compounds and molecular compounds are considered to be what? Great insulators, okay? Yeah, it's crazy. All right, moving on. So they also have low melting point and boiling points. I always tell my students, think of organic compounds, think of butter, plastics. Okay, well, those things may be solids and be molecular solids, a fancy word for organic solids, but they have low melting points. And they do so because they have the weakest forces of attraction because again, you have to pick up those subliminal messages, okay? But they have low melting points and boiling points because what they have is intermolecular forces of attractions that are the weakest. Remember, molecules make up covalent compounds. These are little particles, and they stick together by intermolecular forces of attractions. And because most of them, I should say all of them, when they're hydrocarbons are LDFs, okay, therefore they have the weakest types of forces, all right? So here we go. Um, Now, organic compounds is very important, can be either written as a molecular formula, this is C3H8, okay, notice that's what we've been dealing with all year, or a structural formula. A structural formula shows how they bind or bond. So this would be a carbon has 3 H's, and then this carbon has 2 H's. And this sounds weird, but if you look very careful, this is also a structural formula. So this CH3 here is these CH3s. Notice the carbon here has CH2. Now, why does this middle carbon, CH2, have less H's? Well, because it's bonding to 2 other carbons. So if it's using 2 of its bonds, it only has 2 bonds left to bond with the H's. And of course, if you've got what? CH3 at the end, well, it's the reason why you can have one more H is because this carbon's only bonding to 1 carbon, so it's open to bond to 3 H's. So the terminal carbons have the 3 hydrogens bonded to it. And of course, there's another way to show it, what I just had there. So structure is going to be very, very important because we're going to name these chemicals based on their structure. And you say, well, why do we care about the structure so much in organic chemistry? Because as you learn in biology, the structure is, I call it structure is king. You change the three-dimensional structure, you change the properties of the chemical. Everything in biochemistry, biology, okay, organic chemistry is about the three-dimensional structure. In inorganic chemistry, we just cared about what was in the chemical, okay, and how many. But now we're going to deal with the structure, and that's very important as we go forward. Structure is king. It's everything. Think about a protein that acts as an enzyme based upon your understanding of biology. That lock and key model has to have a certain three-dimensional shape. That's the same kind of deal we're dealing with here. You change that shape, okay, even if it has the same molecular structure, you change its properties. Okay, now in table E, okay, we have something called the acetate ion right here. And they draw it as C2H3O2 negative, or they show it as CH3COO. And they say, well, why people always ask me when I'm teaching Regents chemistry, how come they give you these both forms? Well, this is the molecular formula of the acetate ion, and this is the structural formula. Okay, either one can be written, but this is showing that carbon at the end has 3 H's, then it bonds to a carbon, and we're going to find out that this oxygen double bonds with this carbon, all right, and then single bonds with this O to get to its 4, okay? So this is showing the structure. You may not be able to recognize that yet, okay? This is just showing how many. So they give you both here because guess what? Because it's a carbon-based here, this is a carbon-based structure, and because structural formulas are important, this is what we do a lot of times with our organic compounds. We show the structure. And I will show the structure if people are confused by it. All right, so it looks like this. We're going to have a carbon with its 3 H's at the end. Why? Because it can do that because carbon has 4 bonds. It wants to have the octet. Okay, now this carbon is going to bond with another carbon, and we're going to learn this COO ending. This is a carbonyl carbon. It's going to double bond to an O, and then it's going to go to an O here. And it's negative charge because, well, there used to be an H here, okay, and that H left, okay, and it's acetic acid. In fact, this is vinegar, or this is what we call the conjugate acid of vinegar, right? So an H left, and now it's positive. But you can see how this carbon has 4 bonds, all right? Any case, that's the structure there. All right, so on to the homologous series of hydrocarbons. Homologous just means the same family. That means we have a series of hydrocarbons. Hydrocarbons just means we have molecules that just have carbons and hydrogens, and they're in the same family. And here are the family names: alkanes, alkenes, alkynes, and benzene, although benzene's not part of the curriculum. Okay, but these are the same type of hydrocarbons based upon their bonding between the carbons. We're going to get to that soon. All right, and they have a particular type of pattern of adding hydrogens, and therefore a particular general formula that we'll get to, and that'll be happening in what we call table Q. So let's kind of move on here. Okay, so in a homologous series of hydrocarbons, if you're in the same type of family, and those are the alkanes, alkenes, and alkynes, what we know is that as they get bigger, okay, their boiling points and freezing points increase due to the increased number of LDFs. Now, if I'm in a regions class, we just tell you that, okay, but generally speaking, LDFs, or London dispersion forces, increase in strength when the cloud of electrons gets bigger. So if you add more carbons and hydrogens to your carbon-based chain, you're going to increase the cloud of electrons. And remember, LDFs are those momentary movement, that distortion of the cloud that makes these temporary dipole moments. Bottom line is, the more electrons you have, the stronger those momentary dipoles, or the stronger the LDFs. So as long as you're in the same type of family, and we'll figure that out soon, no worries, as you add more hydrocarbons, they get bigger, okay? And hopefully no one's sitting in front of you. So moving on. So here we are, and by the way, this family name are alkanes. Now you say, well, how do I know these are alkanes? Well, we'll get to that, but alkanes have single bonds between the carbons, which means that the carbon chain is going to have the max amount of H's. Okay, notice as we add a carbon, we're adding 2 more H's, and okay, and we'll get to that. But the bottom line here is, as we add more carbons, what's happening to the boiling points? They're increasing, and they're increasing because their LDF forces are increasing. Okay, in fact, notice the 4. This is methane, this is ethane, propane, and butane, and these are 4 gases of hydrocarbons, and then become liquids, okay, and eventually the octanes. The bottom line here is that the boiling points increase as the carbon chain gets bigger, okay, and again, we know why in AP chemistry or more advanced courses if you're doing this outside of the Regents curriculum. But for the Regents curriculum, hey, more carbons, okay, to the chain, a bigger boiling point, greater LDF forces. So here comes the first question, and this could be a typical question on a Regents test. Okay, which of the following hydrocarbons has the largest boiling point? Okay, well, if you don't know, the great Grotsky or the not so great Grotsky will tell you. So let's look at the choices: C10H22, C11H24, C13H28, C12H26. Well, based on what I taught you, the more carbons in your chain, okay, and I'm not pulling your chain here, the more carbons in your chain, okay, the greater the LDF force is, the more strength of forces between each individual molecule, the harder it is to pull apart. Therefore, the boiling point will be greater with the greater number of carbons. And I believe that's choice C. Let's see what the great Grotsky thinks. And so he's going to come by and stop at the right answer. And there it is, okay? All right, moving on. So now, as we talk adding organic chemistry, as we talk, we're talking about this idea of a naming system, because we have to name these molecules, and these molecules are named based on their structure. Why? Because structure is everything in organic chemistry. So we're going to replace an old system. Before, we had this IUPAC naming system, which basically was a conference where a bunch of chemists got together and agreed how we would name this. I'm sure it was an interesting time, a great party. They came up with an international way, okay, to name these compounds. Before we had this consortium or this convention of naming molecules based upon their structure, there was common names. And because they find organic compounds every day, and because 99.9% of all molecules are organic, there was just too many of them to try to remember all the individual names people were giving the compounds. So we couldn't use common names, although there's still some common names that are old that stay with them. We went to a system that describes their structure so that when we find and discover a new organic compound, and it happens every day, they're so numerous, we know its name immediately if we know its structure. Okay, that's very important. All right, so here's an example of ethine. There's two parts to this parent name here. The first part is the longest continuous chain of carbons. And notice there's two here. And if you go to table P, you're going to notice that's an F, and that's a prefix. And the F tells me how many carbons are my longest continuous chain. And the suffix at the end, the YNE, tells me how many bonds are between the carbon. And that is in table Q. And so we have ethine, eth for two carbons, YNE because they're triple bonds between the carbon. Now acetylene was that old common name. Notice C2H2 is the molecular formula, and here is the structure. Okay, so any case, as I mentioned before, the IUPAC naming system is based upon the prefix and suffix. The prefix, okay, is listed in table P. Table P will list meth, eth, prop, but, pent, hex, hept, okay, for 7, oct for 9, non for 10, non for 9, sorry, dec for 10. And then if you go to table Q, it's going to show you single bonded and in anes, enes and ines. So we started this discussion talking about alkanes, alkenes, and alkynes. Single bonded hydrocarbons, double bonded, and triple bonded. So table P and Q are your friends here in your region-based formula. And there they are, okay, in all its glory. All right, so if I've got, 7 continuous bonded carbons in my hydrocarbon, it starts with a hept. And if they're single bonded between the carbons, it's heptane. If they're triple bonded, heptyne. If they're double bonded, heptene. Okay, very important. Looking at me, hopefully. So, as we go through this, okay, we have these two other words that pop up. We have this word saturated and we have unsaturated hydrocarbon. This is a Rob McMahon many years ago, great student. He actually petitioned to have AP chemistry in our class many years ago. Thanks, Rob. He's now a doctor. Good for him. All right, now, medical doctor. Any case, alkanes in table Q have this general formula, CnH2n plus 2. And so ethane, what is 2 carbons based on table P, and then it's going to have 1, 2, 3, 4, 5, 6 H's if you draw it. And if you notice the formula, CnH2n plus 2, what does that mean? Well, if I have 2 carbons, and we have 2 carbons, I times it by 2 and add 2 to get the hydrogens. Well, 2 times 2 is 4, plus 2 is 6. This formula always works if I have a hydrocarbon that's single bonded. And we call this a saturated hydrocarbon. Why? Because it's holding on to the maximum amount of H's. And saturated fats are fats that have single bonded carbons because they're dealing with saturated hydrocarbons. All right. Unsaturated are alkenes and alkynes. These are the ones that have double and triple bonds. And they're unsaturated because they have under the amount of the maximum H's. Notice this is C2H6. This is C2H4. How come I have 2 less H's? Notice the general formula here, CnH2n plus 2, Cn2n. I lost the plus 2. As I add a bond between the carbons, I have to lose 2 H's because carbon must make 4 bonds. Count with me. 1, 2, 3, 4. The 3 and 4 is the double bond in the middle. So if I have to maintain my 4 bonds, and we do for the carbon, it can't bond with the 2 H's. So 2 H's, each H from each carbon has to be lost to make this happen. Notice alkynes with the triple bond. This is C2H2. So it actually has 2 less than the ethene. So as we go from an ethane, saturated, the maximum amount of H's holding, to an ethene and ethyne, we lose 2 H's as we add an extra bond. So it goes CnH2n plus 2, CnH2n, CnH2n minus 2. As we add another bond between the carbon, we have to change the general formula to having 2 less H's. CnH2n plus 2, that's the maximally held. CnH2n lost the plus 2 because we added a bond, and then CnH2n minus 2 lost 2 more because we added additional bond. These two down here, party people, okay, all your unsaturated, okay? And what Rob is showing you is that if you rotate them, it's interesting to note that when you rotate something that's single bonded, okay, it can rotate in its fixed position. Okay, and of course I'm talking here, and so I'm showing you how we can actually rotate from this single bond. Notice this single bond's in his hands here. Okay, it's one of my first chemistry classes. And then if you have a double bond, now it doesn't quite look like this, but this is an alkene. Okay, if this is 1, 2, 3, 4, that'd be bute and butene. Okay, if we rotate this, okay, it's gonna have to load, I guess. It doesn't rotate freely because that double bond, which we all know in a more advanced chemistry class, is a pi bond, and it won't rotate. Okay, so unsaturated fats have hydrocarbons that don't rotate, and they tend to be safer because they don't rotate into a ball, as we'll see. Okay, so this is 1, 2, 3, 4, 5. You go to table P, that's pent, and I'm just showing the rotation there. All right, let's continue on. So alkanes, as I just mentioned, are saturated due to the fact that each carbon is holding on to the max amount of hydrogens. That's because every carbon is bonded. C3H8, and we can name this. Look at table P in your Regents chemistry. If you don't have them handy, I'll have them printed. Okay. 3 is prop, right? And of course, propane because of single bonds. Now, C3H8, look at the general formula. Double the amount of carbons, 6 add 2, and this is 8 H's. 1, 2, 3, 4, 5, 6, 7, 8. So if this has 3 carbons and it's single bonded or it's saturated or an alkane, it must have 8 hydrogens. All right. So there's table Q. And as I said before, table Q is also your friend here, as it shows you as we go from ethane, 2 carbons, ethene for a double bond, and ethyne for the triple bond. And we lose H's as we add carbons because they become under the maximum. These are unsaturated. Unsaturated fats have double or triple. These guys can't rotate, as I showed you. These guys can. Okay, so here is the general formula. All right, but it's the alkanes are the saturated. Let's move on. So if we have fatty acids, now fatty acids, we're going to learn, have a carboxylic acid ending. This is called a Q group. This is not a hydrocarbon, but we're going to get there eventually. This is called a saturated fatty acid because we have carbons that are single bonded. Don't get worried about the up and down nature. The up and down nature is showing that this is a tetrahedral. But the bottom line is every carbon, look at my bond here, has a single bond between the carbons. Okay, and so this is a saturated, this is an alkane type of scenario. Notice here we've got a double bond here. So this has 2 less H's. Okay, and there you go for the type of molecule it has. Notice this is C 16O2, this is C18, so you can't compare the H's directly, but this is losing an H that should be here and here in order to double bond here, so this is unsaturated. So unsaturated fatty acids have a double bond, and polyunsaturated have more than one, okay? So interesting enough, okay, let's look at a saturated fat. Now saturated fats have what? Single bonds between their carbons. So if I play this, okay, what can happen in a saturated fat is once this loads, is that because they can turn on every carbon bond eventually, so that thing can turn on itself. Think of, I showed you Rob bending the corner, but think of every carbon bending onto itself. This can ball up and pack, and this is not really what you want in your bloodstream, right? This could possibly, okay, clot, or not clot, but could block a passageway, and that's not a good thing in your circulatory system. So we consider saturated fats that come from animals, hello, okay, animal fats, not to be good for us. Now, unsaturated fats come from, of course, plants, as we showed in the last slide. Okay, if I go backward, so going backward, I can see that palmitic acid is a saturated fat, and the oleic acid, okay, is the unsaturated. Okay, and this, of course, comes from what? The plants, and this comes from saturated animals. All right, so moving forward. Let's play the unsaturated fat. This, of course, has got double bonds, many. This is a poly unsaturated fat. And as I showed you with Rob, it can't what? It can't move. And because of those double bonds, it can't move, and not having to be able to rotate. And therefore it doesn't, well, it won't block your arteries or veins as quickly. So it's more of a safer fat to have in your system. All right, moving forward. All right, so let's name this compound. All right. First step is what? How many carbons? Go to table P. There are 3. And so therefore, going to table P, we see it's a prop. That's the prefix. What kind of bonds exist between the carbons? Well, there are single bonds. And therefore, it ends from table Q and ane. That's simple, guys. Really. Okay, what's the name of this hydrocarbon? Well, obviously, it only has 1 carbon, so we ask ourselves how many carbons. And you go to table P and you see the prefix is a meth. And because it's not bonding to any of the carbon, it can't be a double or a triple, so it has to be a single bond. Go to table Q. What's the name of a single bond? Okay, and that, of course, would be the ane. All right, so methane. So you notice the naming, this is the IUPAC naming system, is describing the structure because structure is king. So name this hydrocarbon. Should be an easy one. How many carbons? Therefore, it's the eth for 2 carbons from table P, and single bonds between the carbons, ane. So simple. Sometimes. All right, so here is another question. Typical Regents level, New York State Regents question. Which of the following hydrocarbons is a saturated hydrocarbon? Now, being saturated means you're holding on to the maximum number of H's. It's screaming to you that it is a what? An alkane, right? You're looking for an alkane. Now, you could draw these out to see if they're single bond, or you can use the general formula. All right, and so if I was to draw, okay, let's say C2H4, let's say I didn't know any better, and most of the time I don't, okay, and I'll try to draw. So let's do C2H4. I draw a C here and another C, and then I put the 4 H's all the way around. And I know this is given to you, but if I draw it, this doesn't seem to be right because every carbon must have what? 1, 2, 3, 4 bonds. There's nothing else. There's 2 H's and 2 C's. The carbons must have another bond. So party people, this must have a double bond right here. And that's a terrible color to use. All right, so this must have a double bond here. That's the only way to work it. And by the way, in table Q, what's the formula? CNH2N. For an alkene, you always double the amount of H's as carbons. So this is not the choice, okay? And C2H2 would only work if you had what? Carbon with what? Triple bonds to have just 1 H, okay? So which one follows the general formula of an alkene? Where we double, remember it's CnH2n plus 2. Okay, well, it's going to erase all of this, and let's see what the great Grodsky thinks. He'll come by and tell us the answer. And there it is. Okay, Grodsky with hair. C4H10. It's the only one there that has what? That has single bonds between the carbons. And if you were to draw it out, okay, if you were to draw it out, C4, put 4 C's because that's what's there, and you have single bonds between the carbons. Every carbon has to have what? 4 bonds. So you put some dashes that represent the H's, and you can count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4 C's. All right, moving forward. Okay, isomer is very important because structure is king. If you notice, these guys right here have the same what? Chemical formula, the same molecular formula. In inorganic chemistry, that would mean they're the same thing. But no, in organic chemistry, structures can be different. Therefore, their properties are different. We call this isomers. Isomers are structural isomers we study here in Regents chemistry, and these are the what? Same chemical formula, molecular formula, same number of carbons and hydrogens, or same number of atoms and type, but a different arrangement. Changing the arrangement changes their properties. In a more advanced chemistry course, you would know that this would have what? Weaker LDF forces and have different properties in this. So you have something that has different properties. How can it be the same chemical, right? So even though they have the same number of stuff and type of atoms, they're going to have different properties. We need a different name, okay? And that's where we're headed now, okay? So isomers, structure is king. Here's another example, okay? This is called 1-propanol. We're going to learn the 1. We have propane, prop for 3 carbons, ane because there's single bond. We take the E away, we add OL. I'll teach you this later in the second lecture. The OL is for an OH group. We're telling you that we're putting the OH group on the first carbon. Here we're putting the OH group on the second carbon. They both have the same what? The same molecular formula, but different structures. This is an isomer, okay? And this is important. This could get you intoxicated, probably with an upset stomach, because it's a lot like ethanol. Ethanol is the alcohol in beer, wine, liquor, right? But this structure is lethal in 8.5 ounces. Okay, so note this is rubbing alcohol, and people have been known to drink this thinking it was alcohol, and they've either blinded themselves or killed themselves. So this you could ingest and not be lethal. This one could kill you only because of where you put the OH group. By the way, these OH groups are not bases. These are covalently bonded, okay, hydroxyl groups that we'll learn about. But these are alcohols. So the placement and the structure gives it its property. Structure is king. Having the same chemical formula is not good enough. That's why the naming system I am just started teaching you is based upon structure. And this is telling me that the alcohol groups on the first, this is telling me the alcohol groups on the second. They are different compounds. They better have different names because they have far different properties because of their structure. Okay, so that's what an isomer is. Same molecular formula, different structure. So here we go. Now, this is important. Which of the following hydrocarbons has the largest number of isomers? Okay, think about that for a second. Largest number of isomers. What it means, how many different structures can you have? Well, if you think about it, the more carbons you have, couldn't you have more arrangements? The less carbons you have, the less different arrangements you can have. Remember, an isomer is having a different structure, a different arrangement of the same type and number of atoms. So it makes sense that the larger you are, the more carbons you have. Let's see if the great Grodsky agrees. So the one with the largest number of isomers should be the one with the greater number of carbons. So let's see what the great Grodsky thinks. And he's going to stop at the right answer. And there he is, C5H12. Okay, let's take a break. Break's over, moving on. So now you guys figure this one out. Which of the following hydrocarbons is an isomer, okay, of this structure right here? So I want an isomer. Based on what I taught you, you should know what an isomer is. So which of the following choices is an isomer of that? I'll give you a couple of seconds so you can pause the video. All right. Well, we have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. C is not an isomer. It's the exact same thing. So if you count 1, 2, 3, 4, 5, and the same number of H's, let's see if you agree. Bring on the great Grodsky. And there it is. Choice D is an isomer. Different structure, same number of carbons and hydrogens. Okay, here's a past advanced placement question. Look at this one. Okay, this is an old question when organic chemistry was on the course. Which of the following structural form represents an isomer of the compound that has a structural form represented above? Okay, let's see which one you guys think it is. You can pause the video now. All right, I'm going to tell you what the answer is. Okay, and so the answer is right there. Okay, choice B. We're putting the bromide in different positions. Some people pick choice A, but if you pick up and flip, pick up. Think about these are three-dimensional structures that we're drawing two-dimensionally. But if you pick up um, the structure I drew you right here, okay, and flip it, you get this one. So A and this one are the same structure. Okay, all right, and we're almost done here. And then cyclocompounds, and we're going to stop here. All right. So this will be enough for this part. The next lecture will finish out this lecture. Oh, I hope that helped.